Good afternoon, ladies and gentlemen. My name is Alexakis. I'm a structural engineer. I'm a research associate in infrastructure monitoring and modeling. I'm working with CSIC. And I'm going to talk about aging infrastructure, and in particular, old masonry railway bridges, and how we can develop tools for better asset management and operation. There is an urgent need for maintenance protection of aging infrastructure. Consider, for example, that 50% of railway bridges are masonry arch bridges in the UK, right? And their maintenance is critical for the safety and the economic well-being of people. And at the same time, these structures have an important cultural value. But there is a challenge for the engineers. The challenge is that, from one hand, a bridge collapse can have a major socioeconomic impact, but from the other hand, it's very difficult to predict it, because in reality, we have a very limited understanding of how the structures behave. And our structural analysis model have a high level of uncertainty, right? So what's the solution to this problem? In CSIC, we believe that the solution to this problem is to participate in the upcoming digital revolution, a revolution that gradually changes the way we live and the way we conduct research. We are surrounded by big data, and the new challenge now is to find an effective way to use this data, right? So better sensing systems means more data, big data, right? So we want to combine our experience in advanced sensing with big data analytics and work with the Alan Turing Institute at the Imperial College, bringing together civil engineers and statisticians, right? And that's the core idea behind this project, the long-term monitoring of a Victorian viaduct in Leeds. This is a very important bridge in Leeds next to the central railway station, which is significantly damaged due to the increase of operation train loads and due to environmental effects. And this is why an extensive repair was conducted by Network Rail in 2015. Our long-term monitoring system comprises a fiber optic network that measures at 80 different locations the dynamic deformation of the bridge every time a train is passing. And at the same time, we have acoustic emission sensors for detection of cracking and high sensitivity accelerometers. Now, by comparing old and new fiber optic signals for the exact same train loading, we're able to find there is an increase that has happened in specific locations, an increase of the dynamic deformation of the bridge. And exactly in these locations, we have the formation of new cracking, right? So by combining signal processing and statistical analysis, you can do the same observations for many different locations in the bridge at the same time, right? So in this graph, we can detect statistically significant changes of the behavior of the bridge. And actually at a very early stage, because fiber optic sensors are very sensitive sensors. What are the next steps? We have to quantify these sensors through physically based modeling, and at the same time, we want to work with the Alan Turing Institute at Imperial College towards the direction of the data-centric engineering, meaning we want to develop real-time structural alert systems. And with this technology, we believe that we can have better asset management, because we will be able to locate and quantify progressive damage at an early stage. We will be able to assess the effectiveness of previous intervention, such as the one in 2015, or make better operational decisions. For example, reconsider train speed limits over the bridge. Poor maintenance and lack of monitoring can lead to natural disasters. And if we don't learn from our mistakes, more tragedies like the one in Italy that happened a few weeks ago might occur, right? So thank you very much for your attention.